we are moving to new topic, which is topic number 4, is analysis and design of resonant inverter and resonant converter. Okay. This topic consists of 2 sections. Section 10. In this section, we will be discussing sinusoidal analysis and design of LLC inverter. And in later section, I introduce one interesting example, application example of this LLC resonant tank to implement a ultra low profile series resonant converter. That will be very interesting. Okay. So first section is this one, sinusoidal analysis and the design of LLC converter. As I mentioned several times, this LLC resonant tank is mostly widely used now because we are using the MOSFET switches. Okay, so this structure is best suited topology for the MOSFET switches. And again, we are talking about the inverter, but same story applies to the converters with extremely minor modifications. They are almost the same, except some scaling of some parameters. Okay, so we have here full bridge series resonant inverter. So we have full bridge switch network, and this is LLC resonant tank, and it has transformer, isolation transformer, and this is R, is the load. Okay, so this current gotta be sinusoidal wave, and this voltage is also sinusoidal wave. If you rectify this sinusoidal wave using some rectifier and you attach the low pass filter, that becomes resonant converter. Okay, so you know this. If you look through this circuit, at this point, you are seeing R prime, which is R divided by N squared. N is the turns ratio of this transformer. We went through this in the last lecture. It's very easy to remember and to derive. So you should remember this. N is here, then N comes here, and in the denominator with the squared. Okay, so then this is the first harmonic model. So we have CLS, series inductor, parallel inductor, and R prime, which is reflective version of real load resistance R. And sometimes we use I here. Okay, this is the current. Right, this current and this voltage will be different from the current voltage measured here. So, but sometimes we use this notation interchangeably, right? So, but you won't confuse with this, right? So we use this VNI, and VT1 is the fundamental component of this tank voltage, and this is just the coefficient of Fourier series of the fundamental component of this scale wave. Okay, so you remember this, 4 divided pi is here. Then it becomes power stage dynamics of, this is inverter, resonant inverter. So here we have this CLS LP in parallel with R prime, which is R divided by N squared. So with this, take a look at the GI characteristics. We went through this several times, so very easy. First one is GI infinity with this output port open. Then this input impedance is just this series connection of 3 components. So we have this is R prime is infinity, and this resistance is, this impedance was defined GI infinity previously. And this one with R prime equals 0 or R equals 0, they are same thing. Was GI 0 in previous notation, right? So with this is open. So there are resonance between 3 components. That resonance frequency here, F infinity, and frequency is given by this inside of this square root to C and LS plus LP. They are in series. Okay? So you have this one. And frequency of this is relatively low because this is large. Okay? And another one is with this one. So this is shorted. Then we have resonance between two components, which is this, and that there is resonant frequency F0. Given by this, it comes at higher frequencies because this L, effective L, is reduced. Right? So this is GI infinity, and this is GI0. Okay? And in between, all the impedances corresponding to the R prime from 0 to infinity is confined in these two regions. Okay, we went through this. Right? So it looks like this. And in the middle, there is one point where all the impedance curves merge together and passing through the other region through this narrow gap, a small pinhole. That frequency is FM. This frequency is very important. And we also derive expression of that frequency as given by this. Right? So this one comes first, and this one comes in the middle, and F0 comes last, obviously, because of the difference between this value of inductance in the equation. All right? So you know this. This is the borderline between good line node efficiency and poor line node efficiency. Idea of this thing is very simple. When R is increasing in this direction, in this region, R is increasing larger R prime, right? If R is increasing, this current, load current, will be very small, right? Then if R is increasing, this magnitude of input impedance is increasing as well, then makes this tank current very small. Okay? So this reduced, then this should be reduced. Okay? Suppose this is reduced, but if this IT is increasing, there is a huge conduction loss. All right? That is the case for this region. Below this line, when R is increasing, so R prime starts from 0 and goes to the infinity, this direction, then this GI, magnitude of GI, is decreasing. That means what? This tank current is increasing, while this load current is decreasing. That is the worst scenario. So this is the borderline for the good line node efficiency and poor line node efficiency. So as I said, I was wondered when I was studying this first time, why people are worrying about this line node efficiency. And later on, I found because of this is very important for the resonant inverter and the resonant converter. So we want to operate the inverter or converter in this region. Okay? So in this region, you have this slope, positive slope of input impedance, means we have GBS characteristics. And in here, the situation is the opposite. So we have GCS, which is bad for the MOSFET transistor. In between, for large R is this one. Then this slope means we have GBS here and GCS here, right? So there are two borderlines, maybe three borderlines. This is a borderline for line node efficiency and borderline for GBS, GCS, and in between we have the combination of GBS and GCS. Okay? So this is the review of the previous lecture, and you should remember this, right? This provides a lot of information about the operation and design of tank network. Okay? This is very critical. And another thing, GCS and GBS boundary was obvious, right? So right-hand side of this line, we have GBS, and left-hand side of this, you have GCS. In between, it can be GBS and GCS. But there are definite borderline. So this is the line for the R critical. So this is the R critical. Blue line, above this line, this value is R. So R is large. So above this line, we have GBS, and below this line, we have GCS. And we can evaluate this curve, simple analysis of this resonant tank circuit. All right. We have another curve, which is R match. R match is the value of the R that maximizes the power transfer through the tank circuit. So this is also important curve, which is shown in red here. All right. So we need to have some relationship with these values. These things is output impedance of this tank circuit, and this is this was a mistake. Should be GI. Okay. So those kind of information is important. Somehow this morning I decided to delete things. This thing is confusing, right? So delete this. Okay. I made several mistakes here. First mistake is this should be F infinity, not F0. And this one should be F0, not F infinity. Okay. So it is rather confusing. We have R prime and R. R prime is this one. Just because of the presence of the transformer, R prime is given by R divided by N squared. So if we consider this as an inverter circuit or inverter model, then everything should be expressed as R critical prime. Okay? This value is different from the R. R is the real load. Secondary side of the transformer is their location. But we are talking about everything in the primary side of transformer. So I was confused with this. So be careful with this, all right? So R match is the value of the R, which allows the maximum power to be transferred. But we are seeing this circuit in the primary side. So R match prime is, we know this, right? This is the same as the output impedance of the tank seen through this terminal, right? That's one thing. And R critical. We are looking at the circuit in the primary side. So we have R critical prime is given by this GO0. Then we derive this, right? GI infinity divided by GI0. Okay? Suppose if in the frequency range, in some frequency range, GI0, magnitude of GI0 is always larger than GI infinity, which is this region. Below this GI0, magnitude of GI0 is always larger than GI infinity. So in this region, then because R match is this one, and R critical is this one, if this ratio inside of the square root is larger than 1, something is bigger than that. If smaller than 1, the other thing is bigger than something. So with this, we have this conclusion. R match is larger than R critical in this region. Maybe previously we defined this region 1 and this is region 2. Okay, so this region, if this sign of inequality is changed, then this sign is changed. Direction of this inequality should be swapped, right? So this is the curve, right? So in here, R match is larger than R critical. And in here, we have the opposite situation. All right. So here you are using the R. Right. So this graph is drawn in the secondary side of transformer. So maybe we move forward and backward, but it really doesn't matter. But you need to change these things to, if you see this in the secondary side of this transformer, you call it R match. Then R match becomes you need this N squared here, right? Because of the transformer, the impedance is scaled, and R critical, you need to have this N squared in front of everything. Okay, we have the same thing here. Okay, so this is just a notation, but this is necessary to avoid the unnecessary confusion later. Okay, we know the expression of these three frequencies, and this is the case for the R infinity, and this is the case for the R0, and we call it GI infinity, and this one GI0, so on, right? Okay, so everything is clarified here. So later on, we'll be using this relationship. Okay, it's not difficult, but it's tricky. If you confuse this, then maybe you will have the further confusions later. Right. Okay. First one is this input impedance characteristics, and the other one is tank transfer function HS is necessary. Okay. So we review this. Right. This is the tank circuit. We have a transformer. R is reflected to the primary side. So this appears as R prime, which is R divided by N squared. Right. So this is V and this is I. So this is the voltage seen at the secondary side. Previously we used the same thing for the waveforms in the primary side. Okay. So don't confuse with that. Okay. It's not good to use V prime and I prime all the time. So I try to avoid that. So you understand this is the waveforms observed at the secondary side. Okay. And maybe the primary side, we use same symbol, but meanings are different. So this is the fundamental component of tank current. And HES is transfer function from this value to output in the secondary side. So I made another mistake here. So this thing, this line below, whole thing is a denominator. It comes in denominator, and numerator is only this one. And we need this N. There's a transformer. I forgot this. So N should come here in between. So N is coming here. Oh boy. Right? Then we have N. We have N. Okay. So this is the expression. This is just the voltage division through this linear circuit. And this is the expression. All right. So don't play with this. I said use the asymptotic behavior of this expression. So first assume this R becomes very large. It approaches the infinity. Then this goes away. This goes away. You only have this and this. Okay. Which is this. Right. So N is here. Right. This is the expression for the voltage transfer gain when this R is infinity, open circuit voltage transfer gain. So we have this. This is the clock of this one. Okay, this one. So this is the expression. First you have this. This is the double integration. So if you plot asymptote, I decided to explain every details about the frequency response for the time being. Okay, maybe some of you are not very familiar with this type of analysis. This is very easy actually. So we have this is double integration. So this slope is increasing by 40 dB per decade. So we use a symbol of +2 to indicate the 40 dB per decade slope, positive slope. So we have +2 slope. This is double integration. We have double pole here. Okay. So this +2 slope is changed, transformed to 0 slope, which is horizontal line. So this is asymptotic flow. Okay, asymptotic flow. And this is the quadratic form with Q of infinity. So here, this S term is missing. That means we have infinity peaking. So Q is infinity, all right? Q, this value, this R is not infinity, but very large. Then this denominator can be factorized into two terms. First one is first order term. Second one is the second order term. So this creates a pole, okay? But this magnitude remains the same, almost same, because the poles are zeros, they are very close, so they cancel, all right? But still, then we have this in the quadratic term, we have the S1 term. That term determines the Q value of this quadratic term. So for that case, Q is given like this, right? So we don't see, if we assume this R price infinity, we cannot evaluate this, but for the previous analysis, factorization business, this Q is expressed like this. Of course, if Q is infinity, this becomes infinity. Then that becomes this one. Simplifies that, okay? This analysis, this simple analysis is based on this equation, exact equation, but that is not a good approach. The better approach is this one. When R is infinity, R prime is infinity, then this is open. The remaining part is only this. Then you can easily write down the transfer function, transfer gain, from here to there, which is just the voltage division of this. And that equation becomes this. Same, okay? The latter one is better, okay? You don't have to play with this, okay? This is a very trivial things, okay? Just wasting of your time. All right, so when this R is large, it shows these characteristics, but because of the Q of infinity, we have infinity peaking here. Then it increase like this, decrease like this, and this is called high pass filter. This low frequency component is attenuated by this, and high frequency component is passed, right? Without any big attenuation. This is something extra. If Q is critically damped, you have this high frequency is just passing freely, and low frequency is attenuated by this much. So it's called high pass filter with high Q. Q is very high. Q of infinity actually. Right? So this is behavior of voltage gain around this frequency. Okay? So this is large, so it comes relatively earlier. This resonance occurs at low frequency, and the other resonance occurs when R becomes very small, R prime becomes very small, so it approaches to 0. So this is 0, very small, then this guy will disappear. Right? So we have this, then this is the transfer function from here to there with this three circuit component, which is this. Right? So initially we have integration, and at the resonant frequency of this one, this should be LS, right? Not L, LS. This should be LS. LS, okay, LS. So this is the resonant frequency, okay? Resonance between this one. If resonance occurs, reactance becomes 0. So this voltage and this voltage should be the same. and gain from here to there is just n. Right? So this value is n. If you sketch just asymptote of this transfer function, so you have this. Okay, so something is wrong. Okay. This one. I should delete this. Right? This is not true. Okay. So we have single differentiation. So increase with plus 1 slope. And here we have double pole. The slope is declining by 2. So plus 1 slope becomes minus 1. So this increasing slope is plus 1, which is 20 dB per decade. This slope is minus 1, which is minus 20 dB per decade. Right? So we have this kind of characteristic. This is called what? This is called bandpass filter. Right? It passes the signal of the frequencies near this resonant frequency. Okay? Maximum gain is 1, just 1, 20 log 1. And the sinusoidal away from this resonant frequency, it is attenuated by this curve. So this is a bandpass filter. And the maximum gain, transfer gain, occurs at the resonant frequency, and maximum value is n. Right? So you combine these two things, and the frequency of this resonance is higher than the previous one because the inductor here is reduced. Just it contains Ls. Previously it was Ls plus Lp. Usually Ls is larger. So we have these characteristics. You combine two things. So this is transfer gain when R prime or R is very small. It starts out from this curve, and if R is increasing, it goes like this, and eventually R approaches to infinity, or R prime approaches infinity. It looks like this. Right? This is the mirror image of the previous LCC converter. Okay? LCC converter, we have opposite situation. This thing occurs here, right? But now this resonance occurs at higher frequencies because we have series connection of the L, then we just add L. We have parallel connection of the L, the composite L, series connection of the L, composite L becomes smaller, so it goes the other way around. Okay? So if you excite that resonant tank, somewhere here, voltage gain is just N. Okay? If you go to very high frequencies, this high frequency asymptote of this thing is this one. This, okay, I forgot to mention this. That is very easy because high frequency asymptote is just the ratio of this coefficient, which is this. Okay? So at very high frequencies, the magnetic curve converges to this value. So by combining those two curves, we have these characteristics, right? So this value is n. So although this gain curve merges to here with the value of n. At high frequency asymptote of this is this one, okay? And this is the other cases. So this is the general behavior of tank transfer function, which is general behavior of DC in, DC out gain of resonant converter. They are same thing. Okay? You have some scaling modification. You need some modification in scaling, but shape is the same. Right? So, what is the desired region of the operation? Okay? So this region is the GBS region. This region is GCS region. So we avoid this. In between, if R is large like this, you have GBS. If R is small like this, you have GCS. All right. So desired region of operation is this one here. You want to avoid this? Let me explain why. Okay. Later on, you will see the slope of this. Slope of this is the gain of some transfer function. Frequency to output transfer function has some gain. Okay, that has the frequency response. that gain is very large, which is desired characteristic. In here, slope is very small or almost zero. That means gain is very small, or even gain becomes very small, flat, right? Almost flat. That means the gain, the gain of control to output transfer function becomes very small. Or if this is the flat, like this, we cannot control output, right? To control output, if you change the operational frequency, this gain should be changed, right? Gain, this value should be changed. But in this frequency range, if you change frequency this much, gain is changing only this much. That means you are losing control, okay? So most people, they operate this LLC converter in this region, okay? Here, this is not GCS. It should be GBS. So this GBS, right? Then slope is fast. Slope is fast. So easy to control. Okay, to modify the some regulation of the out voltage or out current, sinusoidal or DC. You just change the operational frequency in narrow range. But in here, you should change the frequency range this much. Or even it is impossible to change the gain because the slope is very slow. Okay, so this is the desired region of this LLC converter. Okay, I think I asked this question maybe last week. So now I'm answering to that question along with the justification of the answer. You understand this? You should understand this. Okay. So this is the desired region, but the danger of this is if R changes, then GBS will be destroyed. There is the danger of some if this R is changed like this, then operation frequency was here, then with this R, this small R, your converter is in GCS region. So there is some limit, okay? So you should analyze the details about this circuit to avoid that kind of accidental operational scenario. So that is also necessary. All right? So another one, okay? Somehow I'd like to explain the characteristic of output impedance of this tank circuit. So again, we are seeing the circuit in the primary side of transformer. So this is output impedance evaluate with input port shorted. This is important. This occurs as the one critical circuit component in Thevenin's equivalent circuit. Output resistance with input port shorted is very critical information in designing the tank circuit and in predicting the performance of your converter. So somehow this is the expression, right? And this is the expression. So I plot here, forget about this. This might be long or this is unnecessary. Forget about this, right? So start here. Initially we have what? Integration, single integration. So it goes this slope, integration slope. Then here we have double zero. At this resonant frequency, resonance between this C and series connection of the two inductors occurs here. Then this goes up to infinity and come back, right? This is double pole, not double zero. So this double pole is shooting to infinity, then go down. Then you have double zero at here. So it's dipping to the ground, okay? So you have double pole. And double zero with peaking or dipping of infinity. All right. This is the initial. This integration slope, +1 slope, and final slope will be this one, +1 slope again, okay? And forget about this. This is just the asymptotic plot, and this is a frequency, right? Think about this. Here I plot this H infinity, right? So H infinity is transfer function gain of this tank circuit with R prime is infinity. You change this, okay? And I plot this output impedance, input shorted output impedance plot here. So you are seeing two curves together, all right? Suppose switching frequency was here. Switching frequency was here, but with this, we know this VOS, free open circuit voltage, all right? So open circuit voltage, okay, so VOSOC is this VT1 is the fundamental component of tank voltage, sinusoidal component, times this is open circuit voltage, and this open circuit voltage divided by this short circuit output impedance is short circuit current. All right? First, assume frequency was here, switching frequency was here, then you have some value of this which is this one, this purple color. So initially you have VOC here, ISC here. Okay? So we shift the switching frequency to this point, then what will happen? This ellipse equation is shown here. All right? So this is the new point, this blue squared point here. Okay? Then suppose this remains the same, VT1. Obviously, it won't change, and this magnitude of this curve is reduced this much. Okay? This will be reduced. Right? Take a look at this. This ISC, this numerator is reduced. This will be reduced too because of there is a fast slope. So this one is reduced by this much, but this one is reduced this much, which is deeper than this one. Then this is further reduced. Then effect of these two things are this comes in the denominator. So this will be increased. Okay. So if you increase the switching frequency, this becomes smaller, but this becomes larger because this GO0 is decreased further than this one. So due ellipse curve will be like this. Right? So understanding this behavior is also important. Later on, you need this kind of insight of this behavior. So the behavior of this resonant tank is not easy to fully comprehend because of these characteristics. Everything depends on everything else in strange way, in nonlinear fashion. Okay, then makes the design and analysis of this resonant inverter or converter more complicated. Okay, all right. So this is story about the sinusoidal analysis of LCC resonant converter. So we'll go through one specific design example. This design example is not difficult, but very, very tedious and distracting. Maybe you feel this is very complex, complicated, so you need some practice this. So later on, I will provide the midterm exam, which you should follow these steps. We'll discuss today. You will be later track step by step very carefully, okay, to complete your midterm test, right? So this is a very important topic. I think this is the most important part of this story before the midterm exam. Okay? So this is the spec, right? Design specification. This is the input voltage, DC voltage, and this is the output sinusoidal waveform. So this is RMS value, this is the peak value, and this is switching frequency. And switching frequency is given by this 100 kilohertz, and our power is 20 watt. So from this specification, R is given by this VRMS squared divided by this is power, right? Then this 500 ohm is the value of this. Okay, this is the specification, but this is not sufficient. We have another specifications. to determine the circuit component. Here you have a transformer, so we need to determine 4 circuit components. Okay, you should determine this, and this all together. So we need more information. All right. So there is no information. You set up your own requirement. So this is one example. So I want to have this GCF operation guaranteed for the R larger than 500 ohm. That is the example of specification, or maybe it can be your own specifications. Otherwise, it is impossible to determine all the 4 components. Okay, so this is necessary. This is a very practical one. Previously, we assumed the open circuit voltage is given. That was not practical, but this one is very practical. Okay, because you are sure that the R won't go below this value. If you are pretty sure of that, then this can be your specification for your own purpose. So you have specifications. And knowing this, the strategy of design is very important. Okay, how to approach this problem. The critical information for this design is, as I said previously, in the beginning of this lecture, first one is specification, the other one is ellipse equation, last one is Thevenin's parameters. Okay, those 2 things are critical. Without that, you cannot design this. Okay, don't try to design anything without those information. So design strategy is this one. Somehow find this one. This is a transfer gain of tank circuit with output open. All right. So this comes as the first parameter for your Thevenin's equivalent circuit for your converter or inverter, and find out this one. GO output impedance. Evaluate with input port shorted. So first determine this, and from this, with this information, select these values C, LS, LP, and N. 4 parameters need to be determined. So you have 2 conditions. So you determine 2, and to fix the other 2 parameters, you should use your knowledge about operation of this circuit. Okay, engineering insight as necessary to come up with, to determine the other 2. So we'll go through this step by step. Okay. All right. So inverter ellipse. I'm using this notation. Previously it was I magnitude, but now I'm using this I RMS. Okay, it really doesn't matter if I use RMS. Everything should be the RMS. That's fine. All right. So you don't have to use magnitude always. For this design purpose, it is much better use RMS value. This RMS is directly related with output power, so on. So you don't have to play with 1 over square root 2 anymore here. Okay. So this is then the GCS operation for, let me change this. So original target was, delete this, R larger than 500 ohm. Okay, you want to ensure the GCS operation for this value. All right, then R critical should be something smaller than this. Okay, selecting this as R critical is dangerous. So you need some margin. Okay, so with that things in mind, thinking the margin, select R critical as 400. Then you have a margin of 100 ohm. Okay, this is your dear construction, but you select this, so you have some margin for the GBS operation. Okay. Then again, let me delete this. Then R critical prime, because later on we'll analyze this circuit in the primary side of the transformer. So it's better to have this R critical prime. Okay, this is, we know this. GOO is seen by primary side of transformer, and GI infinity is coming here, and GI0 is in the downstairs. Okay, and this should be, this is the R critical. Okay, is the R critical is 400, but we are seeing that R critical in the primary side of transformer. So we should have n squared here. All right. So this equation. So we'll be using this equation to determine this. If this is known, we have some equation. Somehow the product or division of multiplication of this and this can be expressed, this 400 and this number. You select this number wisely, okay? To obtain something good, you select wisely. Suppose you select this number inside of the square root sign 5, then this product of these two things are determined, okay? Then later on, with some other constraint or design consideration, you select this n, right? Then this is determined. Then all the circuit component will be determined based on that, right? So that is the reason why we are doing this. So with this, we have another design, maybe the other design equation. So with this, n squared GO0 squared times GI infinity divided by GI0 is 400. That is same equation written in this manner, right? So, okay. So this page is done, right? So everybody happy with this, right? Then move to the next slide. Next slide. So tank network design. So we know this. This is the sketch of input impedance of the tank, GI infinity, GI0, and this slope is high frequency asymptote is this one, okay, just LS, and this slope is LS plus LP because the resonance are different, all right? We have the common asymptote of SC here at low frequency part, and this is the high, this is the F infinity, FM, and F naught, okay? So desired operational frequency was somewhere here. We decide this based on this tank transfer characteristics. So for good line node efficiency, okay, and the GBS operation, you select this area. So this area is good for the line node efficiency, and in somewhere here, maybe GBS is guaranteed. If R does not reduce below the 400 ohm, then GBS is guaranteed. That is our design goal. But in here, if R is increasing, this is increasing. Then R is increasing. Then tank current is decreasing. All right. So we have the feature of line node efficiency improvement. To maximize that improvement, you should have the considerable distance here in between this one and this one. All right. So this distance is proportional to the margin for the improvement. Right. Previously LCC converter case, we should reduce this because this distance is deteriorating. It is the measure of deteriorating your line node efficiency. Here, this distance is enhancing the measure of enhancing your line node efficiency. So you have sufficient distance here. So you select 5. This ratio is selected as 5. You can select 7, 10, like that. Okay, maybe 5 is a good number. So we select this one as 5. So this ratio is selected based on this consideration. All right. Previously, the ratio between CSCP in LCC case, we used the small number of 3. So we select larger number of 5 here. Then we have this equation number 1. All right. So we need another equation to determine the values of the tank circuit component. All right. So this is equation number 1, very important. And another one is this, we use the inverter ellipse equation. This is inverter ellipse equation written in terms of this RMS value of everything. So everything is in RMS. So this is our design target. Then our power is determined. Then this is determined. All right. Then this value, this I short circuit RMS is V open circuit RMS divided by this GO0. Okay. But we are seeing this value at the output, the secondary side of transformer. So this one is now this VI is defined here, right? So this previously it was defined the primary side of transformer. Now they are defined on the secondary side of transformer. So this is the V, and this is the ISC. Okay, one is the IV at the operating point, and the other one is short circuit, open circuit, right? So you have this, and this is the expression for ISC, short circuit current is open circuit voltage divided by GO infinity times N squared. We know this number. This number we already defined this number in previous slide, which is this. So use this. This is not difficult. It's distracting somehow. So this is determined, right? This is the open circuit voltage RMS value is determined from this inverter ellipse equation. Then this open circuit RMS is this one times input voltage times this turns ratio of transformer, right? So with this is determined. So we determined number 1 and number 2, which is this one, okay? We determined this, basically this one. We have N squared, okay? And another design equation, we determined this one. So we have 2 equations. With these 2 equations, we can determine all the remaining parameters systematically. So to determine, use this one to determine 3 things, right? So we need one additional engineering judgment, engineering insight to determine the turns ratio N, right? So parameter selection. This is the circuit diagram of tank circuit, right? So VT1 RMS is this. Okay, this is the VT1. 4 divided by times in voltage divided by 1 over square divided by square root 2 is VT1 RMS, right? And we know this number. All right? Suppose this LP is much larger than LS. Usually this is the leakage inductance and this is a magnetizing inductance if this is a practical transformer, right? Then this is reasonable. Then the gain from here, assume this one, gain from here to there, assume this is 1, right? Then ratio of this is our voltage. We have desired value of RMS. We have input value of RMS. Then ratio of this becomes the turns ratio of N, right? So if the gain from here to there is just the unity, then turns ratio should be this number, 9.2, right? But usually this is what? This is LLC tank, right? LLC tank has this kind of gain characteristics. Probably the gain at the operating frequency will be larger than unity in general. Okay? That is the assumption. If that is the unity, this is the correct number as n turns ratio of transformer. But usually this gain from here to there is because of this high Q peaking is larger than 1. Then select this n slightly smaller than this one. Maybe I select 7.5. Okay. This is the second engineering judgment. First one is selecting the ratio GI infinity divided by GIO. That ratio is selected for the margin of improvement of low line node efficiency. Another judgment is this one because probably we'll have this tank circuit gain larger than unity, maybe 1.5. Then this is the ideal case when this gain is just 1. Or we don't know exact number, but just select this one for the good educated guess. Okay, that is determined. Then with this, this is determined, right? So this is 9.8. Okay, I think we determined somewhere in previous slide. This one. We select where we determine this. Okay, this is given. We determined this here. Equation number 1, equation number 2. Okay, that's just making things complicated. It's not difficult. It's just bookkeeping business, just to check their notation and their definition. Then you have this. You have this. Then we know this. So this can be evaluated. This n is 7.5. Then this number is determined. Okay, this is the magnitude of this gain with this thing open. That is this one. This is what? This is the series reactance and parallel reactance. It's just the voltage division. So we have this XP, XS, XP. Okay, one equation. And you have another equation here. This was equation number 2 actually. This is equation number 1. Okay, with this is determined, and this value GO0 output impedance seen by the output port with input port shorted is parallel combination of this. Then from this we know this value. Then you have this. So you have two equations here, and you have two unknowns. So that can be solved. Okay. So this is the value. So XS, XP. Okay. Remaining step is just selecting the reactive component to satisfy this equation. Okay. So in here, you should use another brilliant or smart engineering judgment. Okay. So with this XP, parallel reactance is determined LP only. So LP is determined, but series reactance is a combination of this. So LP is determined. Then somehow you select the ratio between LS and LP with some requirements, some judgment. Okay, you should have some justification selecting for that, because we initially selected this. Okay, at switching frequency, magnitude of GI infinity should be 5 times larger than this one. Okay, because to have the gap, sufficient gap for the efficiency improvement. Okay, so we determined that. So this should be guaranteed. Then this initial slope of this, final slope of this impedance should have some distance. What I mean by is that because we have some gap, so this slope, asymptote, should be, slope is the same, but this frequency should be different. So there is some considerable difference between LS and LP, right? So for the 5 times difference at frequency around here, maybe this value, ratio of 2 circuit components can be selected as this number. Okay. You select 6.5, 6.6, 7. Okay. It really doesn't matter. This is just a matter of design trade-off. But there are so many, at least 3 points, you should determine some ratio. Okay. Any ratio might be okay. Then you will have some strange design. Okay. LC will be very large, or GBS, GS region will be bad, or the margin will be very narrow, or the improvement in low line node efficiency will be very small. Okay. To have reasonable performance, you should follow this. Okay. Then XS is given like this. Okay. Then with this is LS is given 6.4 times of this divided by 6.5, determine. Then this is determined. So you have all the component fixed now. So design is done. Okay? So this is the final design of your LLC tank. 0.4 microfarad, 2.5 microhenry, 15 microhenry, 1:75 tons ratio. Okay? This will be a very reasonable design. If you select differently for one ratio, you will have some different value, but that the overall behavior of the resonant tank circuit will be very similar to this. Right? Then to have the desired output voltage, initially the switching frequency was 100 kilohertz. If you modify something, maybe you need shift switching frequency a little bit. Okay. Later on, you simulate this thing, input impedance and voltage gain, then you can judge, oh, this switching frequency should be increased by 2%. That's not a problem at all. Eventually, this thing will be closed loop controlled. Then there should be the frequency response feedback part. That feedback automatically take care of this business for you. Right? So this is the way of designing this tank circuit. I try to find out something else, but this one was, for me, this one looks very reasonable. Okay, so it has some theoretical background, and this is the method. Erickson, the fundamentals of power electronics, that guy proposed. Right? So he didn't provide this explicitly, but behind his discussions, he was implying this. Right? Okay? So maybe we stop here. Right? So next week, we finish up the remaining part of this. Remaining part is very simple because that is the justification or validation of this design procedure, and to check whether this inverter is operating as desired, as targeted. Right? Okay. Right. Thank you.